everyone, and welcome to this evening's Specialist Maths student tutorial. My name is Stephen Crouch, and today we will be looking at mechanics, specifically dynamics. Before we get to question one, we're going to quickly look at a few settings. So the first settings that would be great to have is have our angle in degrees. Most dynamics questions have our angles in degrees, and therefore it's a good idea to have your calculator set to degrees mode. If you're on radians mode, you can simply click the RAD at the top right, and that will convert it to degrees. If you're on the older CX Part 1 CAS, you can click the gear icon at the top right, go to document settings, change radians to degrees, etc. The next thing I'd like to mention as well is that in Specialist Mathematics, the acceleration due to gravity is defined as g meters per second squared, where g is 9.8. This is also stated at the start in the instructions of your exam at the end of the year. So first things first, this is actually from the statics tutorial from a previous tutorial in statics. So I'm just going to quickly revisit and recap some of this, as it will be useful for the next couple of questions. So first things first, forces can be described using vectors because they have both magnitude and direction. So if I take two vectors with forces F1 and F2, and I start moving them around, then the length of the vector describes the size of the force, and the direction of the vector, of course, describes the direction of the force. So if you have two or more forces acting on an object or a particle at a specific point, then you can simply add the forces together to create what we call a net force. So one way to describe this diagram here is what we call a triangle of forces. So the net force is simply the sum, the vector sum rather, of all the forces that are acting on the particle or object. So let's look at our very first question. We have three forces that act on a particle at the origin. So here is a picture of two forces. The first force is a 4 Newton force that acts at an angle of 30 degrees to the x-axis, and it's entirely in the horizontal plane. The second force is a 6 Newton force that acts at an angle of 45 degrees to the positive x-axis, and that is also entirely in the horizontal plane. Finally, we have the third force, which is root 3i plus root 2j plus root 5k, which is not shown on that two-dimensional diagram. So this notes page right here effectively summarizes the information that was in the question. We have F1, F2, and F3. Our job is to figure out the magnitude of the net force. So what I'd like to do first is visualize all three forces. And this is a three-dimensional axis that, as you can see, we have a grid that is only in the XY plane, and the blue and red vectors, which are F1 and F2 respectively, are in the horizontal plane. And then you have this black-colored vector, which is in three-dimensional space. So it's got a K component as well. So we've got a particle or an object that's located at the origin, and these three forces are acting on that particle simultaneously. And our job is to find the magnitude of the net force that acts on this particle. Okay, so first things first, what we're going to do is we are going to convert each of these forces into vector forms. So what I'm going to do is I'm going to say F1, control, and the template button, which says is assigned to, and I'm going to type this in as a vector. So control and open bracket, it gives me a round bracket, not round bracket, sorry, a square bracket. And in that square bracket, we're going to convert 4 newtons at 30 degrees into a three-dimensional vector. So the horizontal component of that force, that is the x-axis direction component of that force, the I direction, is 4 times cos of 30 degrees. Now, given I'm in degrees mode, I don't need to do anything more. I can just type 4 cos 30, then comma. the J component is 4 trig and then sine of 30, and comma, this force F1 is entirely in the horizontal plane and therefore has a 0K component. So that has now defined force F1. In a similar fashion, F2 will be defined as 6 cos 45 degrees, comma, 6 trig again, sine 45 degrees. And finally, again, F2 is in the horizontal plane and therefore has a 0K component. Enter on that one. And finally, F3, we will define that using the vector as it's been stated in the question. So that is square root 3, comma, square root 2, comma, square root of 5. So we now have vectors F1, F2, and F3 all defined. So the net force is defined as the sum of these three. So I simply have to do F1, I can call it NF for net force, and I'll define that as F1 plus F2 plus F3. And now what we have is the entire net force written in exact form. So if the angles were not 30 degrees, 45 degrees, 60 degrees, etc., then this net force would be in decimals. Right. So this net force would be in decimals. So given the fact that we have it in exact form, makes it easier for scenarios such as in exam 1. But given this is a calculator active question, we can actually use our calculator to find the magnitude of the net force. So the way we're going to do that is we're going to press menu, 7 for matrix and vector, and then 7 for norm. That's because the reason behind that is norm represents magnitude. So menu 771 gives us norm, and then we just go to var for variables, and then go to NF for net force. I hit enter, and I get the exact form. I can press Control Enter, and that gives me the answer in decimal form. Now the question states we need this correct to 2 decimal places. So looking at the second decimal place, it's 5. The third decimal place is 7. So that 7 rounds the 5 up to 6. So the answer is 12.36, which you can see right there. That is our first question. It's the very first multiple choice question. So hopefully you got E when you tried out the question as well. Okay, let's move on to the second question. We now have a surfboarder that has a mass of 70 kilograms and is being towed on the end of a rope by a jet ski. So the rope maintains an angle of 5 degrees above the horizontal throughout the first stage of the maneuver. The tension in the rope is T newtons, and there is a total resistance, which is a combination of air and water resistance, of 30 newtons that is acting on the surfboarder. So this is our next question, and there are a few concepts in here that will need to be looked at in further detail. So let's go and look at those things in some detail. The first thing is we need to look at Newton's laws of motion. Now, the first and third laws were looked at in significant detail in the previous tutorial on statics. So in this particular tutorial, we're going to look basically at the second law, which is the core of dynamics. So in Newton's second law, we're looking mainly at unbalanced forces. There are multiple forces acting on an object or a particle, and they are unbalanced. So first, the first law, just as a quick recap, the first law regards an entire net force of 0. So whether there's no force acting on an object, or there's multiple forces and they're all canceling out, the first law simply says that the object will remain stationary or move in a straight line with constant velocity. And the third law simply is the action-reaction law of Newton, which is if one object imparts a force onto another object, and the second object will impart an equal and opposite force back onto the first object. Right, so a couple of forces that will be used a lot throughout the next few examples is, number one is the weight force. So any object that has mass on the surface of the Earth is attracted to the center of the Earth by the force of gravity, and the magnitude of that force is what we call the weight force, which is simply m times g, whereas, as I said before, g is 9.8 meters per second squared, close to the surface of the Earth. Another force that we will see very often is the normal reaction force. So the normal reaction force, as was explained in the previous tutorial, is simply a force that acts perpendicular to the surface, and that is basically the reaction to the gravity force. So for example, if you have a laptop or a book that's sitting on a table, gravity pulls the laptop or the book down into the table, and the table pushes back onto the book with an equal and opposite force. Finally, we have tension, which was just shown in example number 2. So tension is basically forces that act along strings or ropes. So if you pull on an object by using a rope, then basically the tension transfers your applied force towards the object, and the tension is what the tension in the rope or string is what pulls the object forward or in the intended direction. So getting back to our question over here, we now need to look at what parts of the question are required. So the first part of the question says this: write down an equation of motion for the surfboarder, given that the acceleration is a meters per second squared. Okay, so the equation of motion for any object that in a dynamics question is simply a statement that brings together all the forces that are acting on a particle in a particular direction. So it basically is Newton's second law, with all the forces on one side and the mass times the acceleration on the other. So before we get any further, let us actually visually represent these forces. So as you can see, there's the tension force that is pulling the surfboarder, and the tension force is acting along the rope, and that rope is at 5 degrees above the horizontal. So the horizontal is this dashed line over there to show the parallel to the water, and the tension force is 5 degrees above that. We then also have a 70 G force acting downwards, which is the weight force. We then have a 30 Newton force acting to resist the motion, which is the total resistance of air and water. And finally, we have the normal reaction force upwards. What you might notice is that the normal reaction force is basically a bit less than 70 G, and that's because the tension force has a small upwards component, which is reducing the normal reaction force, which would have been 70 G, is reducing it by that little amount. Okay, so that's basically what the scenario over there. So before we write the equation of motion, let's quickly look at the tension force, and let's resolve that into a horizontal and a vertical component. So this arrow here is the tension force, as you can see, and clearly it is 5 degrees above the horizontal. So this tension force is comprised of a vertical component as well as a horizontal component. So the horizontal component, using basic SOHCAHTOA trigonometry, is T cos 5. So if this is the unknown, let's call it X, then cos 5 degrees equals X divided by T, and therefore X would equal T times cos 5 degrees, which is the value, which is the magnitude of the horizontal component of T. What that means is, in terms of the motion of the surfboarder, because the surfboarder will be presumably traveling in a horizontal direction, it is only the horizontal component of T that matters in terms of the acceleration of the surfboarder. So what that means is we have T cos 5 degrees that is pulling this surfboarder forward, basically from the jet ski. It's pulling him forward, and then we have 30 newtons acting backwards. So T cos 5 minus 30 is the net force acting on the surfboarder in the horizontal direction, and that is equal to the mass, which is 70, times their acceleration. So that right there is the equation of motion for the surfboarder. I didn't convert cos5 to decimals because the question did not mention anything about decimals. So this is basically as exact as we can get it. All right, so now that that's done, let's look at part B of the same question. So if A is equal to 3.3, so basically during this first stage of the motion, the surfboarder is accelerating at a rate of 3.3 meters per second squared. Our job is to find the value of the tension correct to the nearest integer. So we have the equation of motion from before, so all we really have to do is type this out again and replace A with 3.3 and simply solve for T. So let's do that. Menu 3.1 is solve, and let's put T times trig cos 5 degrees minus 30 resisting is equal to 70 mass times 3.3 acceleration, and let us solve for the tension and press Control Enter, and we get 261.996977. That is really, really close to 262. So if you were to write this as your answer, you would simply write T equals 262, and then you would put newtons over there. Or in fact, if you look back at the question in the student worksheet, I believe the T had newtons already there. So you can either write T equals 262, or you can put 262 newtons as well. It just depends on the question. Make sure you read every question twice before you move on to the next question. Okay, so we now have a second stage of this surfboarder's motion, and that is the tension is now 300. So comparing that to the previous, we had 262 approximate newtons of tension, and now it has increased to 300. Not only that, you can see that the acceleration has also increased. What we have to do now is find the new angle that the rope now makes with the horizontal. So we've got roughly the same, roughly similar diagram here, except that we now have 300 that's now fixed, it's known. The angle is not known, and everything else, and the acceleration is 3.5. So what we're going to do is we're going to work out a similar equation of motion, and then use that to solve for theta. So our equation of motion would be 300 multiplied by cos of the angle. Now I don't know what the angle is, and I'm just going to call it theta as per the question. So where to find theta? You can press the pi menu, and then theta is the last option in the first row. So 300 times cos theta is the horizontal component of the tension force, minus the resistive force of 30, because the resistance remains the same. There's nothing in the question to state otherwise. And that is equal to 70 times 3.85. So what I've got here is the new equation of motion for the new parameters of the question. So when I hit enter, all I've got really is an equation that has a single variable of theta in it. So all we can do now is simply solve it, keeping in mind that there are domain restrictions. This theta has to, of course, be positive, but also must be less than 90 degrees. So let's solve that, taking that into account. Menu 3.1, and I'm going to press up and then enter, which copies and pastes the same equation. I want to solve that for theta. So comma, and then theta. And we're going to close the bracket, and then control equal, press left to get the vertical line, and then we're going to give it the domain restriction of 0 is less than theta, which is less than 90. Okay, because everything is in degrees, we're going to state it between 0 and 90. I'm going to press Control Enter, and there we go. So correct to one decimal place, the value of theta is 3.3. So we have theta degrees over here, so the value of theta is simply 3.3. Okay, so moving on to the next question. Question 3 is the classical lift problem. So over here, we have a lift, as you can see, and there is a box that is sitting on the floor of that lift. That lift is accelerating upwards at a rate of 3 meters per second squared. And as you can see, we've got a normal reaction force of the floor on the box, and we also have the usual weight due to the gravitational force. So the first thing that you might notice is that the normal reaction force is a lot bigger than in terms of magnitude compared to the weight force, and that is because the net force is acting upwards due to the acceleration being upwards, and hence the normal reaction force is bigger than the weight force. So to solve a question like this, again, we're going to look at the equation of motion for the box. So we have the normal reaction force pushing the box upwards, which is being applied by the floor. We then have the gravitational force pulling the box downwards, and that is the net force, and that equals the mass of it multiplied by the acceleration. So all we have to do is go to our menu 3.1, solve, and N is our normal reaction force, minus 5 times 9.8, which is our weight force, and that equals 5 times 3 for mass times acceleration. Solve for N, and we get 64. And going back to this, as you can see, the answer is C, which is 64 newtons. Now, when you do this in class, you might actually already have equations that give you this answer in one line without going via the equation of motion. But I think it's always a good idea to know where formulas come from rather than blindly applying them. And these lift problems are a perfect example of understanding Newton's laws of motion very well, specifically how a net force comes about when looking at a complex problem. Okay, so now let's move on to our second last question, which is question number 4. This one's a bit more involved, but let's have a look at what it is. So we have a 10-kilogram box that's been pulled along a horizontal surface by an 8-Newton force. And that 8-Newton force is acting at an angle of 27 degrees to the horizontal. This diagram shows all these different forces acting. So as the box moves, we have a resistive force impeding its motion with the magnitude of F resistance equals 0.1 V. So what's going on is, as this box picks up speed, the resistive force increases in magnitude, which leads to the fact that this might be a force that's dependent on basically something like air resistance. So air resistance typically acts in response to velocity. Typically speaking, though, it actually normally reacts to velocity squared, but for simplicity, we just have a linear resistive force. So because of this, because of that variable force, that does bring in something called variable acceleration, which we will look at very soon. So first things first, we're going to write an equation of motion for the box, and hence write a definite integral to evaluate the time taken for the box to reach a speed of 9 meters per second from rest. So what happens is we have this exact scenario over here, and this starts from rest as stated by the question. Because it starts from rest, it will eventually reach a speed of 9 meters per second. And this question is asking us to find the amount of time taken to reach that speed of 9 meters per second via a definite integral. All right, so there's a couple of different concepts in play over here. But first things first, what we might do is have a look at the 3 different variable acceleration formulas. So we have A, which is the acceleration is the derivative of velocity with respect to time, the first derivative. It's also the product of the velocity times the first derivative of velocity with respect to x. And finally, acceleration is also the first derivative with respect to x of half v squared. So one of these will be used, and given the question is talking about the relationship between velocity and time, we will be using the first one, which is a equals dv dt. We might see, you might see an example of the second and third ones in the worksheet. So I hope you've downloaded that, and we'll have a look at those questions. Okay, so we've got this scenario over here. So what we might do is have a look at the equation of motion. So the equation of motion is involved, there's a few parts involved here. We first need to look at the horizontal component of the 8 Newton force. The reason being, this box slides along the horizontal surface, which means it's the horizontal component of all the forces that contribute to its motion. So the forward force, or the force acting in the 8 newtons, is 8 cos 27. So 8 cos 27 minus 0.1 v. 0.1 v is pulling it backwards, and then we can that is equal to the mass of the box times its acceleration. So what we can then do is, I've actually got 0.1 v there, and when you divide by 10, that denominator is actually going to be 100. Let me quickly fix that. I've got 100 there. Right, sorry about that. Right, so as you can see, I've got A equals 80 cos 27 minus V all over 100. So that is the acceleration in terms of the velocity. And what we can see is that I'm equating A to dv dt. So whenever you get to a question like this, A in terms of V, A in terms of X, A in terms of T, a very swift decision needs to be made in terms of which acceleration formula do we equate it to. So the way you do that is you look at the question again, and you see what are you looking at, what are the variables involved. So you got V is the speed, and we've got T is the time. So we're basically finding a relationship between the velocity and the time, which means dv dt is the one used. So then what we can do is we can flip both sides upside down and effectively taking the reciprocal of the equation, and we get dt dv equals 100 over 80 cos 27 degrees minus v. So this now is a differential equation where we have dt dv on the left-hand side. So we are now set up to write a definite integral that will give us the time taken for the box to reach a speed of 9 from rest. And what is that definite integral? It is this one here. It is simply the integral of 100 over 80 cos 27 degrees minus v, integrated with respect to the velocity between 0 and 9. Now, normally we would have a plus and an initial condition at the end, but because we're looking at the amount of time taken from rest to 9 meters per second, we basically, our stopwatch starts at 0. So adding 0 doesn't do anything, and therefore this definite integral will give us the required time. So let us go ahead and actually figure out this definite integral. So go into our calculator, and we've got shift plus is a nice shortcut for definite integrals. 0 is the lower bound, 9 is the upper bound, fraction 100 over 80 cos 27 minus v with respect to v. Let's go Control Enter because we only want an approximate answer, and we get 13.497. The question wants it to 2 decimal places, so our answer is 13.50 seconds. So this box will take 13.50 seconds approximately to reach a speed of 9 meters per second from rest. Okay, so let's look at our very last question for this tutorial. We've now got an inclined plane. So on this inclined plane, we have a box of mass 6 kilograms. As you can see, we have 6g downwards, and it is on a smooth plane inclined to the horizontal at an angle of 30 degrees. It has a light elastic string, light inelastic string attached to it, and then that passes over a smooth pulley. And the string is then also connected to a 4 kilogram box that is hanging freely. So we've got two connected particles, one of them on an inclined plane and the other one hanging freely. So what this question tells us is that at the instant the 4 kg box is moving downwards at 1 meter per second. So what is happening is these are initially at rest, they are released, and then this 4 kilogram box will eventually reach a speed of 1 meter per second. At that stage, the 4 kg box is exactly 7.41 meters above the floor. Our job is to calculate how long it actually takes to reach the floor. So if you think about this question, we don't have any friction or anything else like that, which means that the acceleration of the system will be constant. Right, so what that means is instead of looking at all the different forces and doing them one by one, in the interests of time, I'm going to simply look at the net force on the entire system, divide that by the mass of the entire system, which will tell us the acceleration, and then from the acceleration, we can use constant acceleration formulas to figure out the time taken to reach the bottom. Okay, so what we're going to do is let's look at the net force on the system. We have 4G acting downwards. So here is the diagram again, as you can see. So we have a 4 times 9.8, that is the force acting downwards. And what is impeding that motion is this tension, which, or rather, is the weight force of the 6 kilogram box that is acting down the inclined plane. And the component of that, as explained in the statics tutorial, is going to be 6g sine 30 degrees. So minus 6 times 9.8 times sine of 30 degrees. That right there is the net force. Now, what is the total mass of the system? It is 10 kilograms. So acceleration is going to equal the net force divided by the total mass. And there we go, A equals 49 on 50, or as a decimal if you'd like, 0.98 meters per second squared. Right, so now we've got the acceleration of the system, we need to take an initial speed. We're going to focus on the 4 kilogram object because that is also accelerating at 0.98 meters per second squared. So we have an initial speed of 1 meter per second. So I'll just write that in a comment here. So we have an initial speed, which is most often referred to as u, which is 1. We then have an acceleration of 0.98. By the way, I'm using downwards as the positive direction, given that this motion is all downwards, just for simplicity. So A equals 0.98. We then also know that the distance, which we normally call S, is 7.41 meters, and our job is to find the amount of time it takes to complete that journey. All right, so we got U, A, S, and T. Now, whilst the constant acceleration formulas are not specifically part of the specialist math study design, it is helpful in constant acceleration questions such as these. Of course, we can also solve it via using a differential equation. But for simplicity and in the interest of time, I will do it as a constant acceleration formula. So the formula that we need for this one, again, I'll write it as a comment, is S equals ut plus half a t squared. So that is one of our constant acceleration formulas. And now I'm simply going to use the solve command. Menu 3, 1, solve. So S is 7.41 equals u times t plus a half times a times t squared, comma t. Now, given this is a quadratic, it might be useful to give it a condition that we want our t value to be positive. Hit enter, and there we go. t equals 3. So it takes exactly 3 seconds for this 4-kilogram box to start at 1 meter per second and then land up on the floor 7.41 meters down. That is all we have time for this evening. Thank you very much for joining us. I hope you found this helpful, and we will see you in the next tutorial. Good evening, everyone.